I have a more or less vertical line on the board at the point where the pendulum hangs in its equilibrium position, or at the horizontal position where the pendulum hangs from equilibrium. Pendulum crosses equilibrium, cross, 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 cross. Okay, I get that rhythm down. I think I've got it synchronized. Now I'm going to attempt to drop this domino at the instant the pendulum crosses the equilibrium point, and then see if I can hear and see where the domino is, or where the pendulum is when the domino makes a sound hitting the floor. Are we ready? Let's see, 1, 2. Okay. Now, according to my observations, well, yeah, of course, you've got a video. You can see, did I do this right? Did I really release the domino at the instant the pendulum crossed this line? Okay. Obviously, it's humanly impossible to make that completely simultaneous. So you can maybe stop your video a little bit and see what you think. How well did I do in releasing the domino at the appropriate instant when the pendulum crossed this point? Now, where was the pendulum and how far had it traveled when the domino hit the floor? We heard the sound. Hopefully you heard the sound. It was fairly loud. We have a rubber mat down here. It made a fair amount of noise. The way I saw it, the pendulum had gone over to here and back at just about the instant the sound occurred. I don't think it was completely simultaneous. I actually think, when I looked at it, that the pendulum had gone a little bit beyond this position by the time the domino hit. Okay, well, unsure of that. Okay, how far did the pendulum fall? Well, how far did the domino fall? It fell from about the level of my eye to the level of the floor. Now, if I walk over to the wall in the lab, we have concrete blocks on the walls. I can count 8 blocks right up to just about my eye level. So what I'm thinking is the pendulum, or the domino, fell 8 blocks from rest in half a cycle of that pendulum. Okay, then the average velocity, well, let's back up. What can we determine about the motion from the fact that we fell 8 blocks from rest in half a cycle? Well, we know the initial velocity to have been 0 since it was from rest. We know the displacement to have been 8 blocks downward, and the time to have been 1/2 cycle of that pendulum. So, what's the average velocity of the pendulum, of the block, of the domino? We got pendulums, blocks, and dominoes. Hopefully I can keep them straight. They're quite a bit different from one another and have completely different functions in this situation. Okay, the average velocity is going to be the displacement divided by the time interval. Now, we get that, of course, by using the definition of average velocity is the average rate of change of position with respect to clock time, which is change in position over change in clock time, delta S over delta T, and we've identified delta S to be 8 blocks, delta T to be half a cycle. We then get an average velocity of 16 blocks per cycle. Now, what I really want to know is, assuming the acceleration of that domino to have been constant, what was that acceleration? This is not an answer to what is the average or the acceleration of the domino, average acceleration, or if we assume constant acceleration, just the acceleration. Okay, this is the average velocity. It's not the average acceleration. And I'll note that there's a strong tendency for people to, when given information like this and ask for the acceleration, to calculate the average velocity and think they're done. You have to identify your quantities. You have to go back to definitions in order to efficiently and reliably do that. Okay, so here's our definition. We see clearly that we've got an average velocity here. What's the average acceleration? It's the average rate of change of what? Et cetera, et cetera. What's the average rate of change of velocity with respect to clock time? That's change in velocity divided by change in clock time. It's not average velocity divided by change in clock time. I see that a lot. If you write out the definition in words and write out every word and write it out until every time you use it, until you can think it clearly and understand that you do get delta V over delta T, and don't write it down wrong. Okay? Okay, well, what is the change in velocity? Well, it's final velocity minus initial velocity, and that's going to be divided by the time interval. Okay, well, what is the final velocity? Now, I really would hope that by this point, people will stop just automatically doubling the average velocity when they want to get the final velocity, because people are doing that whether the condition for doing that applies or not. So I'm going to say, okay, well, average velocity by the straight line property of the v versus t graph for uniform acceleration is the average of initial and final velocities. Now, the initial velocity being 0, then this just says that the average velocity is the final velocity over 2. So in this case, where the initial velocity was 0, we have this, and therefore multiplying by 2, the final velocity is double the average velocity. So we've done it. The problem is that people will do it when the initial velocity is not 0, and that leads to obvious unfortunate consequences. Okay, so in this case, we verify the final velocity is twice the average velocity. Average velocity is 16 blocks per cycle, so the final velocity is 32 blocks per cycle. Of course, we're going to subtract 0 to get the change in velocity, and we're going to then divide by delta t, which is half a cycle, and we get 64 blocks per cycle squared. Okay, so the acceleration is 64 blocks per cycle squared. Now, I give you a little more information. Information that a block is, okay, when professionals lay blocks, they do a good job of getting the blocks at uniform spacing of 8 inches, so that each block corresponds to 8 inches of distance. Okay, and a centimeter being an inch being 2.54 centimeters, and a foot being, or 8 inches then, is 8 times 2.54 centimeters. That comes out 20.32 centimeters. And I just round that to 20.3 centimeters. I also commented that using even the 0.3 here, I threw out the 2. I just rounded off to 20.3. I could have just rounded this to 20 and still had less uncertainty or error in this quantity than the idea that my time hit exactly half a cycle. I think I was off by at least 10% on being able to determine that. So with the uncertainty inherent in the way we measured the time here, that difference between 20 centimeters and 20.3 centimeters is insignificant. Okay, well, so a block is 20.3 centimeters. And a cycle, well, now you can go to a timer and time the pendulum. You saw it going back and forth. I think it was pretty close to 1 second, but I didn't actually measure it and I didn't actually time it. But let's just say that that is 1 second with probably a little bit of uncertainty, but I don't think there's a whole lot. So a block is 20.3 centimeters. A cycle is 1 second. So that 64 blocks per cycle squared is 64 times 20.3 centimeters divided by the square of 1 second. And you work out all the units there, you get 1,300 centimeters per second squared. Okay, and that's our measurement of G. My measurement of G, according to the data that I observed. You might observe things more closely and modify that. You could take the information from the video. The one thing you don't know, well, you could measure how long the pendulum took, and you could measure, or you could try to observe exactly where the pendulum was when the domino was released, and exactly where the pendulum was when the domino hit the floor, when you heard the sound of the floor. Of course, there's a little delay in the sound between the floor and the microphone, probably about 3 milliseconds. Okay, now actually it's probably more like 6 milliseconds. Okay, that's our measurement. You could refine our measurement and get a little better one. Most points on the Earth, well, at all points on the surface of the Earth that aren't at the top of really tall mountains, the acceleration of gravity is pretty close to 980 centimeters per second squared. Might vary by 1 or 2 centimeters per second squared from point to point, but it won't vary by much. So our 1300 centimeters per second squared, well, that might not be regarded as a real bad first approximation given the way we measured it. It's entirely plausible that the actual is this and that we had like a 50% error, a 40% error, actually that'd be a 30% error in determining the acceleration of gravity. We will make that determination with more accurate experiments later. Again, our acceleration of gravity based on this data was determined to be 1300 centimeters per second squared, and that's about 30% higher than the generally accepted value. That doesn't mean that the acceleration here really was 1300 centimeters per second squared. It means that very likely, unless there's some kind of anomaly in the fabric of space-time or something, we were just off by about 30%.